We'll start with asking ourselves, why do we even need models for software development? And what exactly we mean by having a model for software development. Consider this example. Assume we want to build a house rental website. So how do we actually proceed with doing that? If we have a large team. If we proceed to provide 3 features like searching over houses or previewing properties and actually contacting house owners for rental, how do we implement this? So there's a bunch of decisions that need to be made when we're starting development. So do we start to work on everything simultaneously? Do we roll out one feature at a time? What can we do to make our product usable from day one of development? So rolling out features as we develop them. Are there any other feature that the customer needs that is, has he told us everything, or there's more to come? So a huge number of people over the years have spent an enormous amount of time on trying to decide on such questions in software engineering. And during that time, some noticed that there were problems with the methods that people were conventionally using. For example, development wandered off on the wrong path, programmers didn't test their code, or the project took so long that by the time it was finished, the customer's needs have changed. So different models try to be asking questions like, do we need that, and do we need that in our development process? For example, do we actually want to roll out one feature at a time, and so on and forth, and they try to come up with an answer. So different approaches try to address these problems, and they propose different methodologies. So ultimately, your practical goal with a software development process model would be to create a workflow that a team can use. This would typically contribute to producing higher quality software reasonably close to on time and within your budget. Well, you will notice that we will be looking at a lot of these workflows, and you might be asking yourself a question, so why are there so many models? So the answer is they tend to emphasize one part of development or another. For example, agile methods allow a project's goals to change over time to track changing customer needs, or test-driven development that forces programmers to write tests for their code. This is one reason for the existence of a variety of different models, but others are there too, like tailoring the development models to the needs of an organization or just selecting the one that you like the most. Let's try to come up with some classification of the process models and characterize them. One way of classifying models might be viewing them as either predictive or adaptive. In a predictive development model, you predict in advance what needs to be done, and then you go out and do it. So you gotta have a good understanding of the requirements. So that supposes that customers know already and exactly what they want. You go through all of the phases like development and testing and deployment in one shot. So as an analogy, you build a brick wall with a predictive model based on past experience. And from that experience, you know exactly how long it is going to take to build a wall of the desired size. You can easily calculate how many bricks you need, then you can order the bricks, schedule some masons, and get the job done. So unfortunately, it's often hard to predict exactly what a software application needs to do and how you should build it ahead of time. So an adaptive development model enables you to change the project's goals if necessary during development, right? So the workflow then goes like this. So customers have some idea or some vision of what they want, and you start building something just to start, and As you go, customers provide you feedback, and you can change what you're building to accommodate for the feedback. For an analogy of an adaptive model, consider a typical research project. It starts with an insight, so let's investigate, say, these bacteria. You know some of the things that you need to do anyway, like collect data and perform modeling and analyze results, but you don't know exactly where the research will lead. You follow the first clue and it leads to a second, which leads to a third, and so forth. Each time you find a new clue, you update the direction of the research. This is also similar to a criminal investigation. Another way of classifying models is to say that a model can be incremental or iterative. An iterative project might not be incremental, in fact. So incremental development means that you have a good idea of what you need, but you build in increments, meaning that you only deliver a subset of the functionality at a time. While iterative development means that you build on top of simpler existing products to provide a more complete functionality that was going to be replaced as you progress with building and as versions of the software progresses. So iterative is not necessarily incremental. As an analog, consider progressive versus baseline JPEG method. So JPEG is a metaphor compressing images. So for incremental development, just like for baseline JPEG, the product you're building is rolled out gradually, one feature at a time, and these features are fully complete, but the overall product is likely not usable because of the lack of the other features that are not there yet. For iterative development, we provide all features but at a low but usable completeness. Therefore, at any moment, our product is 100% ready, although the level of completeness may be like 4%. So depending on the available time, the project can be worked out to the pixel, or it can be left at the stage of some conceptual sketching. So that gives you some flexibility in where you're going. Getting back to our house rental website example, we can use a notion of fidelity, meaning the completeness of the feature to characterize how we would apply different approaches. For example, a low fidelity real estate search screen might let you search for houses by price, but while a high fidelity version would let you search by price or square feet, number of bedrooms, number of bathrooms, and so on and forth. So the predictive model typically provides all features at the same time with full fidelity, but only at the end of your project. An iterative model initially provides all features at a low but usable fidelity. Later iterations provide higher and higher fidelity until all of the features are complete. So incremental model provides initially the fewest possible features for a usable applications. So these features are prioritized in some way, but all of the present features are provided with full fidelity. Later versions add more features, always at full fidelity. One approach that we still haven't talked about is Agile, which initially provides the fewest possible features at low fidelity. Later versions thus improve the fidelity of existing features and add new features. So eventually, all of the functionality is provided at full fidelity, which is, by the way, true for all of these models. So different process models are ways to organize the workflow of your team. And so basically to increase chances of producing high quality software reasonably quickly and cost effectively. So we have seen that these models are typically characterized by being either predictive or adaptive and incremental or iterative or agile. So they typically also presuppose a number of conditions that we will be talking about later today. So let's get our hands on the predictive models first. We'll start with examining Waterfall, the model, and the Sashimi. Waterfall is the plain vanilla of the predictive model world. It assumes that you finish each step completely and thoroughly before you move on to the next step. To this end, you iterate requirements, and then design, implementation, testing, deployment, and maintenance, one strictly after another. So note the clean delineation of the phases in this process, and that's called waterfall because, well, you can imagine water cascading from one step to the other. Of course, waterfall models, they work reasonably well when the requirements are precisely known in advance, and also they include no unresolved high-risk items and won't change much during development. The team has previous experience with building some similar project, so they know what's involved in building the applications. And also, you have to have enough time to do everything sequentially, meaning that the customer is okay to wait until the full application is delivered. Of course, Waterfall is a very predictive model in terms of what we have been discussing previously, and meaning that the requirements, you have to know them upfront, but it's also a very efficient process because it's simple and robust. You have no loops or feedbacks or things like that. So it's pretty straightforward in this sense. Of course, as a con, it's not super flexible, and it can't, afford changing the requirements, and you can't do an early release or get value during the development process from the already running version of the application. Of course, it's easy to imagine, including a feedback loop injected into this model, as one might encounter problems during one of the stages. For example, if you encounter an issue during the implementation that you can't resolve, what you do is you basically go back one stage, that is to the design stage, and you make changes until they are resolved. And if you cannot resolve the changes at the design stage because the requirements are not correct, then you have to go back one step further and change the requirements. Of course, this typically costs something. At least it costs some time, and the development halts, and that's called waterfall with feedback. The Sashimi model is the second model that we'll talk about. It's the also called the Sashimi waterfall, or waterfall with overlapping phases. Is similar to the waterfall model, except that the steps are allowed to overlap, much as the thin slices of fish overlap in the Japanese dish sashimi. So the idea of the sashimi model is that in a project's first phase, some requirements will be defined while you're still working on others, because, well, you have a bunch of requirements to implement, and probably you only have a limited capacity in developing these requirements. And this means that you deliver some requirements while others are still a work in progress. And at that point, some of the team members can start designing the defined features while others continue working on the remaining requirements. And also, you are also having some limited capacity to design and architecture your system. So this means that the design for some parts of the application will be more or less finished, but the design of the other parts of the system won't be. This means that at some point, some developers can start writing code for the designed parts of the system, while others continue working on the rest of the design tasks, and possibly even on remaining requirements. So that's called the Sashimi waterfall, or waterfall with overlapping phases. And of course, it works reasonably well when your requirements are more or less known in advance, but and also what you can basically do is you can start the design before the full set of requirements is fully finished, and architects start working on the completed subset of requirements, and the developers can start coding and things like that. And of course, it's a pretty predictive model, so you still have to know all of your requirements up front. But what it allows you to do is it allows you to shorten your development time, because you can start, doing things simultaneously by people with different skills who can start doing work before it's fully finished in the previous stage. But of course, if you start working on the next stage while you're still refactoring some things on the previous stage, so this leaves you a possibility of rework, because if you have coded half of your application, and then the design suddenly changed, then you have to make adjustments in the development process and make adjustments in the testing process, and so on and forth. So that may result in rework in later phases if previous phases basically get complete. V model is basically a waterfall that's been bent into V shape, as shown here. So what you could previously do is you could basically go from some idea or concept and develop some requirements, and go from design and implementation, testing, and deployment. But the problem was that typically you only start testing and verifying your system once a significant portion of the system has been developed, and so there's typically a need to test earlier in the process. So what you can do is you can bend this waterfall model into a V shape, as shown here. And so the tasks on the left side of the V, they kind of break the application down from its highest conceptual level into more and more detailed tasks as you keep developing the architecture and the high level and low level design down to the implementation. So this process of breaking the application down into pieces that you can further refine and implement is called decomposition. So that is the downward facing arrow in this model. And the tasks on the right side of the V consider the finished application at greater and greater levels of abstraction. So for example, at the lowest level, testing basically verifies that the code works. But then at the next level, verification confirms that the application satisfies the requirements. And validation confirms that the application meets the customer's needs. So you sort of start increasing the level of abstraction. You don't care about the code anymore at some point, but what you care about is the functionality, and then is the customer happy with that. So this process of working back up to the conceptual top of the application is called integration. So you're integrating smaller pieces of your development project into larger pieces, controlling this quality at each step. So each of the tasks on the left corresponds to a task on the right with a similar level of abstraction. So at the highest level, the initial concept corresponds to operation and maintenance, of course. And on the next level, the requirements correspond quite directly to verification, validation, and testing basically confirms that the design worked. So this is what you could do. And so let's discuss about how this V model looks like and when it works and when it doesn't. So the goal of the V model is more or less to shorten the time for testing by basically cascading the validation of software on multiple levels. So you emphasize validation earlier in the process, and by allowing for the steps on the upward facing side of the V to basically get back to the corresponding steps on the left side of the V. And of course, this is a very predictive model still. You still perform most of the steps basically sequentially, but you get earlier detection of potential problems. And that also may result of a rework in later phases, just as in the similar waterfall models that we have discussed previously. So one way of trying to inject some incremental things, some iterative nature into this waterfall model is the incremental waterfall. And what it is, so instead of having all of the application designed fully, what you can do is you can use a series of separate waterfall cascades. So each cascade ends with the delivery of a usable application, and so each cascade works on a separate feature or a subset of features, and it's typically called the increment. For instance, increment 1 here is supposed to deliver version 1 of the application with a number of features. So as you can see, most of the stages that you do are still the same. So you basically more or less follow the same waterfall model. So what you can now do is you can basically allow for the second increment here to basically overlap in time with the first increment, but be built by partially the different team. Right, so if you understand what you need to do in the next iteration, you don't need to wait until the current iteration is completely finished before you start writing new requirements and start designing and things like that. And the same is for the third increment. One particularly interesting thing that what you can do is you can use any of the waterfall variations for each of the increments. For instance, in this example, we have like 2 vanilla waterfalls, and the second one is Sashimi, and that's reflected in this diagram here. So this is what you can do. So incremental waterfall models basically build an increment with all of the waterfall steps burnt in into this increment, and then they switch to another one. So these increments are typically overlapping to allow for delivering the value earlier, and you can use different models for each of the increments. So one advantage of having this incremental kind of model is to deliver feedback earlier, because you deliver partial product, and you can already have the user test it and see if he's like it or not. And also maybe you can already deploy part of the product so that the organization who is the customer of the product can start getting value from that. So oftentimes, though, you don't know about some of the requirements early in the phase. So one general recommendation is that if your organization may benefit from getting partial work done early, you can use this model. Predictive software development has big advantages. It's predictable, encourages a lot of upfront design, and gives a certain inevitability to a project. Unfortunately, this inevitability can lead to either success or failure. If the design is correct and everything stays on track, the project is like a luxury train rolling majestically into Grand Central Station. However, if something goes wrong, the project is more like a train engulfed in flames and speeding toward a dynamited bridge. So why iterative software development? To understand that, we first need to figure out what predictive models can do. In fact, they're really inherently ill-suited to handle unexpected change. They can deal with small changes such as customers deciding they want combo boxes instead of list boxes in their forms, but they don't handle big changes well, such as customers deciding they want 20 extra reports that are all viewable on a desktop computer or tablet or smartphone. They also don't handle fuzzy requirements well. Unless you nail down the requirements precisely at the beginning of the project, it's impossible to create a solid schedule. This means you have to spend a lot of effort at the beginning figuring out exactly what they will do. Imagine, building a new shopping mall and you don't really know exactly where it will be or what it will be like, but start building it and we'll work out the details later. So that's not how it goes. For the iterative models, though, it's easier to address change by building the application incrementally, starting with the smallest, reasonably useful program. And subsequently, they use a series of increments to add more features to the program until it's finished, if it's ever finished, like with web search that is sort of being developed over and over again. Because each increment has a relatively small duration compared to a predictive project, you're committed to a smaller amount of work. So if you decide that the project is heading in the wrong direction, you need to stop only the most recent increment and start with a new one instead of canceling the whole project and starting over. Iterative models also handle fuzzy requirements reasonably well. So if you're unsure of some of the application's requirements, you can start building the parts that you do understand and figure out the rest later. Sometimes you'll learn things building the first part of the system that will make the rest of the requirements clearer. The spiral model is a classical iterative model that proceeds in a series of phases. In the first phase, which some call the planning phase, you determine the objectives of the current cycle. You define any alternatives and constraints in the objectives. In the second phase, which some call the risk analysis phase, you perform risk analysis to determine what the biggest risk factors are that could prevent you from achieving this cycle's objectives. You then resolve the risks and build a prototype to achieve your objectives. This may not be a program. For example, if the goal of the current cycle is to build requirements, then this will be a set of prototype requirements. In the third phase, which some call the engineering phase, you use the prototype that you just built to evaluate your solution. You perform simulations and model specific problems to see if you're on the right track. You might run a bunch of operational scenarios to see if the prototype requirements can handle them, and you use what you learn to achieve the original objectives. After this phase, you should have something concrete to show for your efforts. In the fourth phase, which some call the evaluation, you evaluate your progress so far and make sure that the project's major stakeholders agree that the solution you came up with is correct and that the project should continue. If you decide that you've made a mistake, you run another lap around the spiral to fix whatever problems remain. This all is embedded into each of the software development lifecycle phases. Let us consider an example project using machine learning, the self-driving taxi service. As you may understand, any ML/AI/vision-powered project these days is going to be a high-risk project, hence the spiral model being relevant here. The first objective would typically be to determine user needs and formulate the requirements. Perhaps being able to deliver the taxi service transfer between points A and B is the primary user requirement for the system. Exploring the alternatives to achieving this, one might end up formulating two significantly different sets of requirements. So, for example, either demand from the system a fully automated driving in unconstrained environments, or require from the system to support navigation using additional hardware installations in the city. The risk analysis would expose risks linked with both these alternatives. For example, user safety requirements may need to be refined if driving in unconstrained environments is preferred. The primary goal of this stage is to ensure that these risks are reduced and to produce the requirements prototype depicted in a white box. For instance, extra effort may be put into detailing what users mean by safety. So is it safety for passengers or pedestrians, overall safe driving, or reduced accident rate? The prototype is next validated by team members to ensure correctness, and the prototype requirements become actual requirements. By demonstrating the validated requirements to the customer, the team obtains a green light for the next phase. The next trip around the spiral builds the system design. The team evaluates hardware and software design alternatives, identifies and resolves the major risks, and builds a prototype design. Team members analyze the design and verify that it makes sense. The prototype design then becomes the actual design. The final trip around the spiral drives the application's implementation. The team evaluates implementation alternatives, even though they are probably used to a particular development approach already. They identify risks, perhaps previous projects had bad performance issues, and resolve them, like having more code reviews. The team then builds an operational prototype that shows how the program will work. As you have seen, the spiral model is a risk-driven cyclic approach, where we do only as much as needed to lower the risk at a particular stage. In fact, this is not a process, but rather a process generator, where you can use other models within the turns of the spiral. The spiral has adopted the designation for a number of project deadlines, called milestones. You'll see these milestones being used throughout other models as well. When the stakeholders agree that the project's technical and management approach is defined enough to satisfy all the stakeholders' goals, then it has reached its life cycle objectives milestone. When the stakeholders agree that the project's approach can satisfy the goals and all significant risks has been eliminated or mitigated, then it has reached its lifecycle architecture milestone. And when there has been sufficient preparation to satisfy everyone's goals, then the project has reached its initial operational capability milestone and can be released. The spiral approach is considered one of the most useful and flexible development approaches. The following list summarizes some of its main advantages. Its spiral structure gives stakeholders a lot of points for review and making go or no-go decisions. It emphasizes risk analysis. If you identify and resolve risks correctly, it should lead to eventual success and can accommodate change reasonably well. Simply make any necessary changes and then run through a cycle to identify and resolve any risks they create. Estimates such as time and effort required become more accurate over time as cycles are finished and risks are removed from the project. However, the following list summarizes some of the spiral approach's biggest disadvantages. It's complicated, which isn't always worth the effort, particularly for low-risk projects. Because it's complicated, it often requires more resources than simpler approaches. Stakeholders must have the time and skills needed to review the project periodically to make sure that each cycle is completed satisfactorily. It doesn't work well with small projects. You could end up spending more time on risk analysis that you'd need to build the entire application with a simpler approach. Having said that, the general recommendation would be to use the spiral with very large, high-risk projects. Despite its name, Unified Process, or UP, isn't actually a process. Instead, it's an iterative and incremental development framework that you can customize to fit your business and your projects. So it's divided into two axes, or it has two dimensions. The x-axis defines certain phases and goes over time, with steps like inception, elaboration, construction, and transition. And then the familiar software development process shows up on the y-axis. So among others, we have the requirements, analysis, design, implementation, and test. The amount of gray area under the curve defines how much effort you put during each phase into each process step. Let's look at this process in greater detail. During the inception phase, you come up with the project's idea. This should be a short phase where you provide a business case, identify risks, provide an initial schedule, and sketch out the project's general goals. You want to answer questions like, does it make sense? Is it even possible? What is it that we're building? Maybe we should buy it or have someone build it for us. During the elaboration phase, you create the project requirements. You build use cases, architectural diagrams, and class hierarchies. You need to specify the system, but you still don't want to restrict developers with unnecessarily detailed requirements. The main goals are to identify and address risks, so that the project doesn't fail later. Normally, this phase is divided into several iterations, with the first addressing the most important risks. Key questions asked here are: what can go wrong? How can we mitigate or resolve risks? How are we going to build the system? And how to validate what we're building? During the construction phase, you write, test, and debug the code. This phase is divided into several iterations, each of which ends with a tested, high-quality working executable program that you can release to the users. The iterations implement the most important features first. During the transition phase, you transfer the project to customers and the long-term maintenance team. Based on feedback from users, you might make changes and refinements and then release a new version, so this phase can include several iterations. This phase includes all the usual transitioning tasks, such as staging, building the user environment, computers, networks or coffee machines, and so forth, user documentation, and user training. So the unified process is a framework, not a process, and you can use any model during any phase. Moreover, any step requires all or most of the phases in the process, but emphasizes one steps but not the others. Because you are working with developing typically complex projects, you are going to be using an architecture-centric approach, putting emphasis on the decisions made during construction. You would also typically use use case scenarios and a lot of documentation, such as UML diagrams, in this process. UP focuses on risk mitigation and addresses higher priority risks first. Let's talk about some of the qualities of this approach. Because you're typically thinking about architecture ahead of time, you will encourage quality and reuse of code and other materials in your project. You're also trying to mitigate a lot of risks, which brings more chances for success of the venture. It flexibly incorporates other software development models within itself. One problem with RUP is that it's complicated and needs typically more resources, and it's also typically too heavy for small projects. The recommendation would be to use the UP in bigger and riskier projects where only partially requirements are known upfront. And also, you could benefit from delivering the application incrementally instead of shipping all of it at once. Now let's talk about the framework that's called the Agile software development. So you might have seen and might have heard about it a lot, and it's been widely used recently. And let's just talk about the general Agile framework and its principles, and then let's consider a couple of implementations of that framework, specifically Scrum and Kanban methodologies. So why do we need Agile development if we already have a number of software development techniques? So a lot of problems in software it actually arise in verification phase. For instance, sometimes pieces just don't work together or interfere, or they can also be turned out like this, that you don't expect things to end up this way, or neither did users or customers, and that leads to some dissatisfaction. And predicting user needs is difficult, and sometimes has no more chances. That's, basically fortune telling, and it's known to be hard. And analysts, architects, and developers all introduce their own interpretation of user needs. Moreover, that misinterpretation has a lot to do with never-ending market shift. So, for instance, whoever needs a phone without a camera these days, and throughout the years, as the number of software development efforts increased, this led to the emergence of something called the Agile manifesto. In fact, Agile is more like a mindset, not a framework. So the first thing to consider would be the Agile manifesto, which is in fact a description of the principles underlying the Agile mindset. So in around 2000, a number of successful software development practitioners came together and formulated and were discussing things that went right or went wrong during their projects, and they came up with this Agile manifesto that reads like this: individuals and interactions over processes and tools, working software over comprehensive documents, customer collaboration over contract negotiation, and responding to change over following a plan. So these are the four Agile values that are commonly needed. In this lesson, I'm not going to go much deeper on the overall mindset of Agile and the philosophy of it. If you want to know more, I encourage you to stop the video, click the link in the slide or in the description, and go ahead watching the Agile Values Explained video. Along with the four Agile values, these software development gurus, they introduced the 12 Agile principles. Some of these are read like embrace change and motivate individual or face-to-face communication, and there's no need to read no need to read it out loud. Instead, if you want to know more about it, I encourage you to click the link in the slide or in the description and go ahead watching the 12 Agile Principles video. And rather than that, I will talk about implementing the Agile mindset and with frameworks like Scrum and Kanban. So let's go ahead and consider the Scrum Agile framework. Scrum Agile framework. In Scrum, the development process shifts away from the traditional waterfall model to an incremental software delivery strategy. A Scrum project creates a series of time-boxed incremental iterations, which are usually called sprints. In traditional Scrum, a sprint is 30 days long, although some people prefer shorter sprints of 1, 2, or 3 weeks. The goal of each sprint is to deliver a version of the software that may have limited functionality but still be usable in some way, often called the potentially shippable product. You could actually deploy a PSI to the users, although you may want to wait and release a version of the application when there are enough new features. Within each sprint, a local objective is defined and implemented by a variant of a mini waterfall method, whichever you prefer. The roles in Scrum are like this. So there's a product owner who actually defines what needs to be done. And so he defines the high-level vision of the product, but operates in the customer terms, not in the technical terms. There's the Scrum Master who basically oversees the development process, and you may view him as a kind of a project manager, but his role is a little bit different. He oversees the Scrum methodology for this particular project and tries to improve the processes of the team. And there's the development team that actually builds software. Let's review the typical sprint pipeline. Before the project begins, project owner talks to all stakeholders and arranges a backlog, which is a list of requirements that need to be implemented, ending up with a list of high-level descriptions of what is needed. This is commonly described as user stories. We'll get to what exactly a user story might look like in the requirements video. Next occurs sprint planning, where project owner, Scrum Master, and team select features to be implemented during the current sprint into the sprint backlog. During execution, team performs development, formulating requirements, design, implementing and testing the software. Along that, they iterate on the daily stand-up meetings, talking about progress and resolving issues. As the sprint gets to its completion, a sprint review occurs, where the team and the product owner talk about the product and review the finished work that will accumulate over time into a more complete solution. An internal meeting called the sprint reflection also occurs, where the team talks about the process and how they can be more effective, more productive, or obtain more satisfaction from their work. You can see how Scrum contributes to the implementation of Agile principles. By building iteratively, the team is able to address changes in the requirements and customer needs. Lots of meetings facilitate collaboration between team members, the product owner, and the Scrum Master. The framework encourages continuous improvement with retrospective meetings. You can think of different principles being implemented in Agile in the Scrum framework yourself. The second framework that we are going to be covering is called Kanban. So the actual Kanban framework came and was inspired by the Toyota production process. So it goes pretty much like this. So let's say a team has a process where the work items go from backlog to the design, then implementation, testing, and deployment. And we have asked this team to build a job website which has these features. So you can log in, post a new job, update your CV, and things like that. So let's apply Kanban to this situation. So the first thing that Kanban suggests, or the first property of Kanban, is to visualize your workflow. So let's see how we are going to visualize the workflow. To visualize the workflow, you basically create a visual board. It could be an electronic or it could be a physical board. To visualize the workflow, you place the stages of your pipeline horizontally, and you assign each feature to a particular stage in your pipeline. So once you create this board, then as you work on each of these items, for example, let's say the team is working on post the job and update job, so they will move the item to the design phase. And as work is being done, the work item is moved on the board to represent where each item is. So let's see what the board is going to look like after a few days. As you can see, the problem that may be made easily visible with such a visualization is that a lot of items may pile up at a particular stage, such as the testing stage, causing a potential bottleneck. Thus, Kanban supports additional feature called Limit Work in Progress that says what is the max number of items that can go to a particular phase. For example, you can test 2 items simultaneously at maximum. If you apply these principles, the second principle, then you may end up having a dashboard that looks like this. So if the team is strictly following the limit work in progress principle, the situation wouldn't happen. So let's say the board looks like this at the end of the 10th day. And developer has just got done with make payment and they want to pick another item from the design. So can they move update? Can they move the sign up? Can they move update CV into the implementation column? And the answer is no, because the number of items in implementation is already 2 and the work in progress is 2 as well. To move the sign up feature to testing, we have to deploy update job to login first. Now, if this issue occurs occasionally, then the developers can basically go out and help testing teams test their code. But if this is a permanent problem that will happen again, then you want to manage the flaw. How do we manage the flaw? If it's a permanent resource issue, then we may add more people to the test to basically increase the capacity of the work in progress limits in that particular stage. Or if it's a buggy code, then what can we do in the development so that we don't have that many defects and then it moves faster? Another issue that remains to be solved is to make process policies explicit so that, for example, people know exactly when to mark their items as done so they can move to the next stage. So as you can see, a number of agile principles is being implemented in the Kanban framework as well. For example, visualizing your workflow leads to a simpler understanding of your pipelines and your work process. Limiting work in progress helps maintain a constant pace indefinitely, as does managing the flow. Making process policies explicit helps aid self-organization in teams and motivate individuals because they don't get frustrated and they know what to do at each point in the development process. And it also facilitates face-to-face communication. So to wrap up the Agile methodology, it is indeed a very short course here on Agile. So we have a number of advantages that stem from adaptive nature of software development. For instance, we can detect process problems early and validate user needs earlier in the process. We also can detect integration issues earlier because the process is iterative. And Because we always communicate, we are able to detect translation issues quickly because the language is being used more extensively. Of course, we have also disadvantages because with constant changes like the Agile process, we actually have a lack of control and predictability. It also requires an order, a magnitude more involvement on the customer side because the product owner will have to spend more time on the system. So the general recommendation would be to use the Agile methodology when the requirements may change or the technology is not precisely well explored or even known.